Hello, in this video I will be talking about a reaction of alkenes called oxymercuration demercuration. In the book they refer to it as oxymercuration reduction. Same thing. And this is in section 6.4 in the book, pages 223 through 226. A little bit longer read than some of the other sections, but it's a little bit of a complicated reaction. So please read those pages and then come on back and view the rest of the video. Thank you. So, this particular reaction, and I say reaction in quotation marks because it's actually two reactions, is what's referred to as a modern reaction. In other words, it uses fairly complex reagents, usually gives pretty good yields. In some cases they're expensive, in some cases they're dangerous. So this is actually a two-reaction, one-pot synthesis, meaning that you do a particular reaction in a flask, let that reaction happen, whatever products are form, and then you add another reagent, which then reacts with the product without ever actually isolating the intermediate. So, in this particular case, for example, we start with an alkene, and I've shown propylene here as an example, but any alkene will do this reaction. First thing you do is react it with mercury acetate. I'll talk a little bit more about that reagent here in a minute. In water, as a solvent, and you let that react for a period of time. It's really only a few minutes. And a dramatic color change happens, and then you go ahead and add another reagent called sodium borohydride, and I'll talk about that reagent here in a few minutes as well. And after that reaction is done, again, another interesting color change happens, and you end up with an alcohol. So you've taken an alkene and turned it into an alcohol. Again, quick, easy, high-yield reaction. It's dangerous because one of the byproducts here is mercury, as you can see, because this is a mercury reagent. But one thing you'll notice about this reaction is if you've studied the hydration reaction, which hopefully you have because it was one of the first ones we did, you remember that what happens with hydration is you take an alkene, you add water, just plain old water with a strong acid catalyst, and you add the water across the double bond, hydrogen to one carbon, OH to the other carbon, and you get, lo and behold, an alcohol, just like you do here. In that reaction, the orientation is Markovnikov. In this reaction, the orientation is Markovnikov. So this essentially does the same thing as that hydration reaction, but the hydration reaction is what they call a classic reaction, one that's been around for many years, uses cheap, readily available reagents, but usually doesn't give very good yields and sometimes takes a long period of time to react. So, developed recently, usually fairly sophisticated reagents, usually high yield and efficient. What does two-step one-pot mean? Well, it means you do two different reactions immediately after each other without ever isolating the intermediate product. Notice that this reaction is Markovnikov in regiospecificity, same thing as hydration, and is non-specific in terms of its stereospecificity, meaning it's not exclusively syn or anti, but both. So here's the question. Why do we need a complicated, expensive, dangerous reaction that does the same thing as hydration does? Well, again, it's because it's efficient, it's because it is quick and gives good yields. This, by the way, shows the hydration reaction, same product in both cases. So here are some examples. You predict the products, so stop the video, write down the starting materials, and write down what you think the products will be. And we'll go to the next slide now. So, take the two carbons of the double bond, add a hydrogen to this one, add an OH to this one, and you get this alcohol. Same thing here. Two carbons of the double bond, add a hydrogen here, and an OH here, so the OH goes on that carbon, and you get an alcohol. And same thing here. You add a hydrogen at that carbon, add an OH at that carbon, and you're done. So, exact same products you would get with hydration. So let's analyze the reagents now. First of all, this thing is kind of weird. HGOAC, the OAC in parentheses with a 2. So this is mercury, and the fact that there are two acetates with it means that's mercury 2. It has a +2 charge. So the official name would be mercury with Roman numeral 2. Acetate. Acetate, if you remember from general chemistry, is, in those days we referred to it as C2H3O2 with a negative charge. This is the acetate group drawn out in a little bit more organic way. It's a CH3 with a C double bond O, O negative. It's the conjugate base of acetic acid, as it turns out. AC is a two-letter abbreviation for this group, the CH3, C double bond O, but not with the oxygen. So if you have the oxygen in there, then it becomes ACO, and if it's negative, it has a negative charge on it. Now just to remind you, this AC abbreviation makes it look like it's an element on the periodic table, but it's not. Actually, AC is an element on the periodic table, but it's called actinium, but that's not what this is. This is the acetyl group. So the AC here is analogous to Me for methyl, or ET for ethyl, or PR for propyl. Organic chemists love these little two-letter abbreviations that make them look like elements, even though they're not. So this reagent, mercury acetate, is a mercury plus 2 with 2 acetates. It's just a fairly simple ionic compound. Now let's analyze sodium borohydride, NaBH4. Well, it's an ionic compound. The sodium is the positive part. Tetrahydroborate, or sometimes called borohydride, is a boron with 4 hydrogens and a negative charge. Here's a little dot structure, a boron with 4 hydrogens. And because boron has a valence of 3, the boron here, even though it has an octet, has 1 extra electron, so therefore it's negative. And this is the borohydride ion. It's not one that you run across real commonly, but it's just a polyatomic ion like many others that you've learned. It does turn out to be a very good reducing agent, and that's what it's going to do in this reaction. Okay, so the first reaction is oxymercuration. What actually happens here? Well, the double bond reacts with the mercury, and the mercury adds on to the less substituted of the 2 carbons of the double bond. So there it is attached there. In so doing, it loses one of its acetates. And so now it only has 1 acetate. Water attaches to the more substituted carbon, tertiary in this case, and puts an OH on there. And the other hydrogen from the water and the other acetate from the mercury acetate go off as acetic acid. So that's a byproduct of the first step. So this is actually the product of the first step of the reaction. Now notice one interesting thing here. This bond is between a carbon and a mercury. Mercury, of course, is a metal. Anytime you have a bond between a carbon and a metal, then you have what's called an organometallic compound. And organometallic compounds tend to be pretty unstable. In fact, it's very hard to isolate this product. It's fine as long as it's in solution for just a few minutes, but otherwise it would decompose over time. So we don't let it decompose. As soon as it gets formed, we immediately add the second reagent. And so this product, the one I wrote up here, is then reacted with the sodium borohydride, and that essentially replaces the mercury with one of the 4 hydrogens. So there's a hydrogen on there in place of the mercury. In terms of balancing the equation, you really need 4 of these to react with every 1 sodium borohydride. So in fact, for each starting material, in terms of figuring out how much starting material would have to use, you'd use 1/4 of an equivalent of sodium borohydride. But in any case, we're not too worried about balancing the equation at this point. We just need to learn that the mercury gets replaced by the hydrogen. Well, then you might wonder what happens to the mercury and its acetate when the hydrogen replaces it on the carbon. The answer is, interestingly, it becomes mercury metal. So literally, mercury metal precipitates out of this reaction. And I've seen it. It's actually really cool because the reaction is kind of like an orange color. It's in a flask. You add the sodium borohydride, and immediately the orange color disappears, and you have these blobs of mercury hanging around in the bottom of the flask. That's because of this. And that, of course, is what makes it dangerous, because you get mercury, and mercury is toxic. Anyway, the net result is the 2 carbons of the double bond. You've now added a hydrogen and an OH. So really all you need to know here is that in the first step, you add the OH to the more substituted carbon and a mercury to the other one, and then you replace the mercury with hydrogen. So the net result is OH and hydrogen. And that finishes this lecture for today.